Okay, so welcome to this next video on tetracycline antibiotics. So in this video what we're going to do is, now that we've finished looking at the translation process, we're going to look at how tetracycline antibiotics work. So all tetracycline antibiotics work by binding to the 30S ribosomal subunit. So I will show them bound to this 30S ribosomal subunit here. So this is a tetracycline antibiotic bound to the 30S ribosomal subunit. And what happens is they stop the amino acyl tRNAs from being able to come in to the A site properly. Well, don't get me wrong, actually. I need to say this very carefully. So, the tetracycline antibiotic has bound to this 30S subunit of the ribosome, basically, and let me just colour it in to make it completely obvious what I'm talking about. So this is supposed to represent the tetracycline molecule. It's bound to the 30S subunit of the ribosome, and what it does is it changes the conformation of the ribosome so that it can no longer move the tRNA, amino acyl tRNA, properly into the correct position. So what happens once the tetracycline is bound is the amino acyl tRNAs with this elongation factor TU and GTP come in to the A site. They do bind to their codon, but the position that the tRNA is held within the ribosome is not correct, basically, because what needs to happen is this tRNA needs to be positioned very carefully within the ribosome so that the peptidyl transferase enzyme can move this amino acid here, or this entire peptide chain as it may be if we're talking about a longer version down here. Okay, so that the peptidyl transferase can transfer the polypeptide in the P site onto this amino acid in the A site so that it can forge the new peptide link, basically. And with tetracycline bound to the 30S subunit, the amino acyl tRNA still comes in, it still binds to its codon on the mRNA, but its position within the ribosome is not correct, basically, and the peptidyl transferase enzyme just cannot perform the reaction because the amino acyl tRNA is just nowhere near the peptidyl transferase enzyme, so it can't transfer these. So even though this still comes in, it still binds, it's not in the correct position, basically, within the ribosome for the ribosome to actually transfer the polypeptide from the tRNA in the P site to the tRNA in the A site, basically, and that blocks the growth of the polypeptide. It stops you from being able to expand your polypeptide, and therefore it halts protein synthesis. And if you stop protein synthesis, then the bacteria is not going to be able to make any proteins. And if a bacteria cell is to divide, basically, it needs to make loads of new proteins. So this really emphasizes the two very important words. Basically, there are two types of antibiotic, roughly. Bactericidal antibiotics, so bactericidal antibiotics, and bacteriostatic antibiotics. Tetracycline antibiotics are what are known as bacteriostatic antibiotics. Bacteriostatic antibiotics are antibiotics which do not kill the bacterial cell. Instead, they just stop it from dividing. So it doesn't die. The ones that are already there don't die, but it stops it from being able to divide. And tetracycline stops it from being able to divide because if a cell is to divide, it needs to produce a huge amount of proteins. And tetracycline antibiotics are going to stop you from being able to produce those proteins. Bactericidal antibiotics are antibiotics which actually kill the bacteria. So they would come in and actually kill the bacteria that are already there. Tetracycline is not an example of a bactericidal antibiotic. Okay, basically, it will only stop the bacteria from dividing, and you might wonder, well, what use is that? Well, it stops the bacterial colony from being able to get any bigger, so it makes the bacterial colony, the bacterial infection that you might have somewhere, more manageable for the immune system. So now what will have to happen is the patient will have to have a healthy immune system that can then kill the bacteria which are already there, because this antibiotic is not going to kill the ones that are already there, it's just going to stop any more from forming. So it relies then on the person having a healthy immune system, which can now, with the help of the antibiotic which is stopping the bacteria from growing, it can now kill the ones that were already there. Okay, so we'll finish with just a few examples of tetracycline antibiotics. So let's write them down here. So there is the original tetracycline. Now the original tetracycline is made by Streptomyces species. So it's made by Streptomyces species. So it's the natural one, basically. Made by Streptomyces. So, Streptomyces. So tetracycline, the original tetracycline, is a natural product, basically, that Streptomyces species of bacteria make in order to in order to compromise the division of other bacteria, basically. So it's a competitive aid, basically. Now there are lots of tetracycline antibiotics which are not this original tetracycline, but which are synthetic chemicals which we have made by modifying the structure of tetracycline. And examples of this include minocycline, and doxycycline. Minocycline and doxycycline, basically. Okay, so those are famous examples of antibiotics they're famous examples of tetracycline antibiotics which are synthetic rather than natural.